I think we should get started. So one of my very significant privileges as director of the CFA is to introduce the clay lecture every year. And part of that privilege is that we've had a history of very strong connection to the clay family itself. And that continues today. We're very privileged to have Lavinia Clay with us and Thomas Clay with us. And Thomas has graciously agreed to say a few words on behalf of the family. So Thomas, please.
Well, thank you, Charles. And I promise everyone there will be a very few words. But as Charles was mentioning, this annual event was really a high point, in particular of my father's year for years and years. And back, before last year, when we could all do this in person, he was always a fixture, sitting in the front row and really always looked forward to it. And it just occurred to me, as we were coming up on the 1-year anniversary of when we all started needing to learn to do these meetings remotely by Zoom, that we certainly a mark on the calendar, and I hope that this is the last one that we'll need to do entirely remotely. Though I hope that, as Charles was saying a few minutes ago, that we're able to preserve some of the benefits of this format and the wider access in future years when we're able to do these back in a lecture hall. So the family has really always enjoyed these lectures. We're very glad to be here today, and I will, as I promised, wrap it up there. Thank you, Charles, and we're very excited.
Thank you. Well, thank you, Thomas. Thank you very much. So now to the main event. So I'm delighted to introduce our Clay Fellow, Dr. Andra Stroe. Andra is a native of Romania, but she was educated in other parts of Europe. She went to Germany, to Bremen, for her undergraduate education, where she got a degree in physics and a degree in Earth and Space Sciences at the Jacobs University in Bremen, graduating in 2010. At which point she went to Cambridge in the UK, the other Cambridge, and got a master's degree in physics in 2011. And then went to Leiden University, a university which we have a long and very strong connection with, and completed her PhD in the Netherlands in 2015. She's kept her standards high. Her first fellowship was an ESA fellow in Garching in Germany through 2018. And then we were able to attract her as a Clay Fellow to the CFA. And she joined us in 2018. So she did have the pleasure of an actual physical experience of being at the CFA before the lockdown started. Our most recent Clay Fellow, Julian Munoz, is joining purely virtually, but at least Julian does know his way around Cambridge. So inspired by Thomas to be brief, I'll just introduce the title: Shocking Tales of Structure Formation, Evolving Galaxies and Black Holes in Evolving Environments. Andra, the floor is yours.
Thank you, Charles, for the very nice introduction. It is so good to be virtually with you all. And it is such an honor to share with you today some exciting new galaxy evolution pathways that I uncovered in galaxy clusters, covering work that I've done over the past few years, as well as some very recent work that was published just in the last few months. This work has been done in collaboration with a number of amazing people, and I would like to particularly highlight the students who work with me on these projects, Joe Cairns, Miriam Husseini, and Courtney Canning. And I would also like to thank the Clay family for their generous gift, which enabled me to pursue this work. Now, one of the most fascinating discoveries in astrophysics is the fine interplay that regulates the interaction between large-scale structure, galaxy formation, and black hole evolution. Star formation, black hole feeding and feedback, gas inflow and outflow, and structure formation are inherently interconnected, but have been historically studied separately. And the goal for my research is to really put together the pieces of this puzzle. And today, I will discuss how panchromatic observations of galaxy clusters can help us understand all of these physical processes occurring over a broad range of spatial scales in a coherent manner, and prepare for ATHENA, Lynx, ELT, GMT, and SKA, which will really push the observational boundaries to the epoch of structure growth. But I would like to share with you why I find galaxy clusters so fascinating. They are really extreme objects, the largest, most massive, densest environments in the universe. And as such, they enable us to study a broad range of physical processes, from star formation to structure formation in these very extreme environments. And although we call them galaxy clusters, only between 1 and 3% of the mass in galaxy clusters is enclosed in galaxies. Each cluster contains between 100 and 1,000 galaxies that are traveling at 1,000 kilometers per second speeds through a hot intra-cluster plasma. This plasma shines bright in the X-ray, and it actually amounts to most of the luminous matter in galaxy clusters, between 10 and 12% of the mass. But actually most of the mass in galaxy clusters is enclosed in dark matter, between 85% and 90% of the mass, bringing the total mass of galaxy clusters to 10 to the 14 up to 10 to the 15 solar masses. And we tend to think about galaxy clusters that they come in two flavors. On the one side, we have relaxed galaxy clusters. These are the clusters that have no recent activity, and they have evolved in a passive way. They have very smooth, featureless, centrally peaked X-ray gas, indicative of a relaxed intercluster medium. And they also have evolved galaxy populations consisting of many passive red ellipticals. On the other side, we have merging galaxy clusters, and these are undergoing an active growth phase. They have, this merging activity induces an extended and messy X-ray gas. And also the galaxy properties emerging clusters is very different from relaxed clusters, as we don't find any prominent red sequence in them. Now, there's been a historical bias towards relaxed galaxy clusters, and why is that? And we can think about relaxed galaxy clusters as kind of the closest thing you will ever get in astrophysics to a spherical Kalman vacuum. They, as I said, are very smooth, featureless. They're much easier to detect than their merging counterparts with their extended, messy intercluster medium and their not so prominent red sequence. However, recent work has shown that about 50% of galaxy clusters, even at redshifts below 1, are actually undergoing a merger. And we know that every local galaxy cluster has undergone at least one major merger in its history. So it's very important to study both of these populations, both the relaxed clusters and the mergers, to get a complete pictures of clusters as a whole. And to understand how we can get to these massive relaxed galaxy clusters in the local universe, we need to go all the way to redshift 6, where the general galaxy cluster area is identifiable as an overdensity. However, only at about redshift of 2 do we actually have a major halo that is dominating. And of course, this is followed with a lot of other mergers, and there's a lot of growth that happens between redshift 2 to redshift 0. And let me just zoom in on one of these galaxy clusters in the nearby universe to illustrate how interesting these nodes of the cosmic web can be. And in order to do this, I will give you the example of the cluster PSZ 2G telephone number. This cluster is a spectacular node of the cosmic web that really shows us how important are multi-wavelength observations for unveiling a complete picture of clusters and to understand their history. The cluster was originally detected in the submillimeter just as a blob. But this blob, it already had a lot of information in it, and it told us that this cluster is a relatively low mass cluster, it's about 4 times 10 to the 14 solar masses. However, with multi-wavelength observations, we know that this cluster is actually undergoing a massive merger between 2 subclusters that collided through each other. And how do we know this? In the pink contrast here, I'm showing you X-ray observations of this cluster. And this is showing you this intra-cluster medium. And you can see that it is extended in the north-south direction, and it has 2 peaks. And this is a clear indication of the 2 subclusters that merge with each other. And the optical observations unveil the galaxy populations in this cluster. And they show us that we have 2 brightest cluster galaxies, each tracing one of the 2 subclusters. And the picture is completed by the radio observations that I'm showing here in the green contours. And this radio emission is showing that we have diffuse radio sources associated with shock waves through the intercluster medium. And what we believe is happening is that as you have these two massive clusters colliding with each other, and as they pass through each other, you form these shock waves ahead of the subcluster. And this is pretty similar to, if you have a dense object going through a medium, you will form a shock wave ahead of the bullet here, and then you also form turbulence in the backflow. And this is exactly what we believe is happening in these cluster mergers as well. And what I would like to really convey to you today is the fact that there's so much physics that we can probe with galaxy clusters if we have these multi-wavelength observations. If we put together, for example, radio observations and X-ray observations, these unveil to us the non-thermal component of the intercluster medium. And this means we can study shocks, turbulence, cosmic rays, and magnetic fields. And together with X-ray observations, they can really show us the thermal component of the intercluster medium as well, and help us understand processes such as heating and cooling. With multi-wavelength observations ranging from radio to X-ray, we can really understand black hole physics and active galactic nuclei, unveil processes such as jets and the feeding of black holes and the feedback that they produce on the intercluster medium and the galaxy, their host galaxy. With multi-wavelength observations, we can really understand past, present, and future star formation in cluster galaxies and understand how galaxy clusters drive galaxy evolution. And as I mentioned, galaxy clusters also contain copious amounts of dark matter, and they've been very successfully used, particularly the merging galaxy clusters, very successfully used to understand the nature of dark matter. For example, how interactive is dark matter with other particles and itself. But beyond just pure cluster astrophysics, clusters are very important for other areas of astronomy as well. They're, of course, crucial for cosmology and scaling relations, and they've been also used very successfully as lenses for high-redshift galaxies to magnify these very faint early galaxies at redshifts 10 and 11. And what I would like to leave you with, if there's one message, is that really we can really tie the microphysics with the macrophysics when you have a complete picture of galaxy clusters. And I put together this little diagram here in the hopes that it will illustrate this point to you. And think about it this way: we have structure formation that is happening on tens of megaparsec scales, and this is driving the growth of clusters through mergers, for example. Then the mergers are heating the intercluster medium, but they're also producing these shocks and turbulence that might cascade to smaller spatial scales and maybe affect inflow of gas into galaxies, maybe triggering star formation. And of course, there's a constant flow of gas between the larger scales and smaller scales for scales relevant for black hole activity. But of course, black holes themselves, they have jets, for example, that propagate on much larger scales than the scale of the black hole, and impact the intercluster medium and produce cosmic rays. So you can really see how in galaxy clusters, you can study processes happening maybe on 100 parsec scales, as well as things happening on 100 megaparsec scales. But today, I would really like to focus on galaxy evolution and clusters. And I would like to answer the question of what drives the evolution of galaxies from young star-forming spirals to passive ellipticals. And why do ellipticals tend to kind of stick together in galaxy clusters? And as it turns out, although in the local universe, only about 5% of galaxies are located in clusters, galaxy clusters are a major driver of galaxy evolution. And they're one of the main factors that takes these blue star-forming gas-rich galaxies with a lot of active star formation and turns them into these passive ellipticals that have relatively low gas reservoirs and little active star formation. And to understand the galaxy populations in relaxed galaxy clusters in the local universe, we need to maybe again think about cluster assembly. When the cluster first forms, you have a lot of mergers between galaxies, building up these very massive central galaxies that end up being the most massive galaxies in the local universe. But as the cluster grows and accretes more matter, there's a lot of infalling gas-rich galaxies that get pre-processed in subgroups in the filamentary planetary structure that surrounds clusters. And particularly when the intercluster medium starts forming, there's a very strong interaction between the galaxy and the intercluster medium. And through the process of, for example, ramp pressure, the gas is being removed from these infalling galaxies. And in the absence of new fuel for star formation, these infalling galaxies experience a shutdown of star formation that is very quick, and just a crossing of the cluster, they already are basically completely transformed into these passive ellipticals. And this is why we end up with these two populations of galaxies in relaxed galaxy clusters, particularly towards the cores of galaxy clusters. The populations tend to be very red and dead, whereas the gas-rich galaxies with active star formation tend to be located towards the outskirts. But as I mentioned, to understand how galaxies evolve in clusters, we need to understand the seeds, the early stages of cluster evolution, because of course our galaxy doesn't just infall from an average cosmic density volume into a massive cluster already formed, but there's a lot of pre-processing that happens in the early seeds, the proto-clusters, the high-redshift clusters, this cosmic web of filaments and accretion that is relevant, and also cluster mergers. As you know, clusters grow and they become even bigger. Maybe this is also a major driver of galaxy evolution as well. In our galaxy here, it's very important, and what I would like to kind of do today is to, in understanding galaxy evolutionary pathways in clusters, I would like to focus on contrasting relaxed cluster environments and disturbed galaxy clusters that are undergoing a major growth phase. And our galaxy here that I put here at the bottom is faced with a difficult choice. Shall it take the well-known evolutionary path in relaxed galaxy clusters where we know what happens? It falls into the cluster, very quickly loses all of its gas, and this shuts down the star formation. Or should it take maybe a more adventurous path in this merging cluster, where this disrupted cluster environment with shocks, turbulence, and strong tidal fields might lead to surprising results? And to answer these questions and to address this contrast between relaxed and merging galaxy clusters, I embarked on an ambitious multi-wavelength photometric and spectroscopic observing campaign to unveil the evolutionary pathways of galaxies in 19 relaxed and merging galaxy clusters at redshifts between 0.15 and 0.3, as well as their large-scale structure. And I call this project Anisala, and this is named as a tribute to the storied Anisala citadel in Dobroja, Romania, close to my hometown. Anisala means new settlement in Turkish and Romanian, and it sits on top of a windswept hill at the crossroads of the Danube Delta and the Pontus Euxinus Sea, which means hospitable sea, or as we all know it today, the Black Sea. And it is forever shaped by these forces of nature. And I believe it stands as a very beautiful metaphor for the ever-evolving galaxy cluster environment and its profound influence on galaxy and black hole evolution. But because we're astronomers and we like acronyms, Anisala can also be understood to mean environmental influence on star formation and AGN through line astrophysics. And my goal for this project was to really study the life cycle of star formation and black hole activity. And in order to do so, to study recent star formation and black hole activity, I'm going to use emission lines, optical emission lines, particularly H-alpha, which is a very good tracer for recent star formation happening on maybe 1 to 10 million years timescales. But we also want to tie this in with star formation happening on longer timescales. And we think about, stars that have evolved and are quite old and have gone supernova, so they blew up. And these we can study with radio emission. But we also want to understand future star formation in these galaxies, and in order to trace these future episodes of star formation, we need to look at the gas reservoirs, particularly neutral gas, which we can trace through H1 observations, and molecular gas, which we can trace with CO observations. Firstly, let's focus on recent star formation and black hole activity in galaxy clusters, as I mentioned, using emission lines. The first part of the Anisala survey was to unveil the pathways for galaxy and black hole evolution through a very large H-alpha survey. I carried out this, the largest narrowband H-alpha survey of galaxy clusters, focusing on selecting active galaxies through their H-alpha emissions. So we went and we gathered data on 19 clusters. And this method has the advantage of being able to very uniformly select galaxies down to a very well understood simple star formation rate. And this enables us to build what we call a luminosity function, in which we can measure what is the density of star forming galaxies at every particular star formation rate. And this is shown in this graph over here, where on the x-axis you can see the H-alpha luminosity, or the star formation rate, as they are correlated linearly. And on the y-axis we have the density. And I'm plotting you here the results from a large survey at redshift 0.2. This is not in clusters, but it's on an average density cosmic volume. And what surprised me here was that both relaxed and merging clusters are actually denser in star formation than an average cosmic volume. And originally I found this to be kind of puzzling, because I thought, okay, indeed clusters are huge overdensities of galaxies, but we know, at least for relaxed clusters, that the fraction of galaxies that are star forming that we would even pick up in our survey is very small. But it seems like it wins. The fact that there's such huge overdensities of galaxies wins over the low fraction of galaxies that are star forming. And we do see this overdensity even in relaxed clusters. But the most important thing that is contained in this figure is the fact that we are finding elevated densities of star-forming galaxies in merging clusters compared to relaxed counterparts. So they have very different behaviors. And we can get a couple of kind of hints of why this is happening by looking at the dependence with cluster-centric radius. And I would like you to focus on the bottom side of this plot. And what this is showing you is the characteristic density of star-forming galaxies as a function of cluster-centric radius. And what we find is that merging galaxy clusters that are shown here in the circles are always overdense in star-forming galaxies compared to the field around them. And this might be indicative of this beautiful cosmic web full of star-forming galaxies, maybe subclusters that still have a lot of star formation in them. By contrast, in relaxed galaxy clusters, you will see that there's a suppression of star formation happening between 1 and 2 megaparsecs from the cosmic core. And this is, of course, not a new result. The suppression of star formation in relaxed galaxy clusters is something that we have known for many, many years. And we, of course, believe that this is an effect of the intercluster medium and this ramp pressure that is removing gas away, and at least in a fraction of galaxies, it's effectively shutting down star formation. But this kind of got me really wondering, okay, how rare are these clusters actually in terms of these overdensities of star-forming galaxies? In order to address this, I conducted the widest narrowband survey of H-alpha at redshift 0.2 in 3 different extragalactic fields. And the area was very large, such that we could overcome cosmic variance and find densities consistent with voids and with maybe clusters as well. But what we find is that there's no, the densities, the average densities are quite similar to relaxed clusters. You can find densities of star-forming galaxies similar to relaxed clusters. However, in our 20 square degrees, we find no field that is as dense in star-forming galaxies as merging galaxy clusters. So it seems mergers are really very special parts of the universe that have a lot of active star formation happening in a small volume. And to investigate the causes of this increased star formation activity in merging clusters and understand its relation to the suppressed star formation in relaxed clusters, the second part of the Anisala project focuses on follow-up spectroscopy of emission line galaxies that we selected through our narrowband survey. And I'm very excited that the first paper exploring the spectroscopy has just been accepted for publication last week, and it's available on the archive this week. We used a total of 4 different instruments, and we covered over 800 galaxies, including 400 very bright H-alpha line emitters. Our sample includes a broad selection of sources in both merging and relaxed galaxy clusters. As you can see here, they span a range in magnitudes and H-alpha luminosities, and a range in cluster-centric distance. However, for the analysis, we fully matched the samples between relaxed and merging clusters by selecting only sources located within within 4.5 megaparsecs of the cluster center, and those with luminosities between 10 to the 40 and 10 to the 42 ergs per second. And because we had such a large sample, it was very important to me to have a uniform way of analyzing all of this data and not bias it, and in order to address this, I built GLEAM, which stands for Galaxy Line Emission and Absorption Modeling. GLEAM is a piece of software that enables you to process large numbers of 1D spectroscopic observations in batch mode, and it fits jointly lines in emission and absorption. And for me, it was very important to have this piece of software that is easy to use for other people as well. So I designed it in such a way that it has a single, very human readable YAML file to configure everything. And it not only does it produce measurements of emission lines and all of their parameters, but it also makes plots for you. It is well integrated with AstroPy. It provides a simple installation with PIP. So if you have a sample of a 1D spectrum and you want to measure emission lines and absorption lines, I encourage you to check out our GitHub page and also to check out the recently accepted paper in the Astronomical Journal. And just to show you the quality of data that we have for the Anisala survey, I'm showing you here the example of the cluster Abell 2254. And in the background, you can see in the pink and purple, the X-ray emission of this cluster, so the intercluster medium. And then in the green, you can see radio emission tracing non-thermal phenomena. And this cluster is very interesting. It's very, very massive. It's 1.5 to 3 times 10 to the 15 solar masses, and it is undergoing a major merger, which is injecting turbulence in the intercluster medium. And all of these filled symbols that you can see here, all of these circles, are H-alpha candidates that we confirm to be cluster members, and we have spectroscopy available through our project, so we can study all of their physical properties. And this is quite typical for all the clusters in our sample. And I mentioned that we had a number of instruments that we used, but the quality of data is very comparable between them. And we, of course, have different types of galaxies as well in our sample. Some of them are dominated by star formation, but some of them have evidence for active galactic nuclei. And some of them, of course, have a mix of emission from both. We classified our galaxies as dominated by star formation, AGN emission, or as composite with contributions from both H2 regions and AGN using the very well-known BPT diagram. We managed to classify 680 sources, of which pure star forming galaxies represent 61% of the sample. 13% are dominated by AGN emission, and the rest are composite. And now that I gave you kind of an introduction to the sample, I'm very excited to share some of the results we found with the survey. And I would like you to first focus on this right-hand plot, which is showing you a different cluster-centric radius. What fraction of emission line galaxies is powered by pure star formation or by AGN emission? And as expected, the AGN and star formation fraction at relaxed cluster outskirts, so we're talking at between 3 to 4 megaparsecs away from the cluster, matches those found in large surveys of the field. However, the fraction of purely star-forming galaxies drops within 3 megaparsecs of the centers of these relaxed clusters, suggesting that galaxies are way more likely to have strong emission lines if they are powered by black hole activity. Now, by contrast, the fraction of line emission that is powered by star formation or AGN stays constant in merging galaxy clusters when compared to relaxed clusters, suggesting a rich environment of filament subgroups and gas-rich galaxies. And now let's focus on this other plot. This is showing you the probability distribution with cluster-centric radius separated by ionization source and by cluster merger status. So this tells you what fraction of galaxies that are supported by star formation and are located in merging clusters are located, let's say, between 0 and 1.5 megaparsecs. And what we find is that the bulk of star formation and AGN activity is actually happening in merging clusters quite close to the core. By contrast, the bulk of emission line galaxies in relaxed clusters tend to be located outside of the core of the cluster. And we find this triggering of AGN and star formation in the infall region, which has also been found in other studies. And the idea would be that ram pressure removes gas from infalling galaxies, reaching to depletion of star formation in a fraction of galaxies, but it can also trigger star formation in this gas behind the galaxy. which means, we can detect these galaxies as star forming. Part of the gas can fall back onto the galaxy and fuel black hole activity. And as I mentioned, this has been found, this triggering by ram pressure in the infill region has been found in other observations and also has been recovered in simulations by some of our colleagues here at the CFA. The galaxies have very different properties between mergers and relaxed clusters when you look at their colors as well. And here I'm showing you distributions with G minus R color, which for the redshift of the clusters in our sample traces the res frame UV minus blue color. And let's focus first on this left-hand plot. This is showing you, again, the fraction of galaxies at different colors. And what we found is that sources with AGN and composite spectral features have redder colors than average as expected. And of course, star-forming galaxies are on average bluer, but we find a very high fraction, or about 35% of galaxies that are star-forming in merging clusters have very extreme blue colors. This other plot is showing you the res frame equivalent width of these galaxies as a function of color. And what we find is that the star-forming galaxies in merging clusters have higher equivalent width of H alpha at all galaxy colors by a factor of 1.5 compared to counterparts in relaxed clusters. Now we know that equivalent width inversely correlates with stellar mass. And in field samples at redshifts similar to our clusters, star-forming galaxies with masses above 10 to the 10 solar masses have res frame H alpha equivalent widths of about 10 to 40 angstrom. The distribution of pure star-forming galaxies in our sample extends to much higher equivalent width, indicating galaxies that have lower masses of maybe 10 to the 8, 10 to the 9 solar masses. We know that equivalent width also correlates with specific star formation rate. So how much star formation do you have divided by the stellar mass of the galaxy? So it seems like these low mass galaxies with large equivalent width have probably large specific star formation rates. And this is even better illustrated in this plot here, where I'm showing you the galaxies in our sample divided by ionization source, so purely star forming and those with AGN contributions. And they're also separated by their parent cluster merger status, so mergers and relaxed clusters. And it seems like merging clusters host a population of continuum faint star forming galaxies with bright H alpha emission lines, which are confirmed to have large spectroscopic equivalent widths, or as I mentioned, specific star formation rate, which we don't really find as much in relaxed galaxy clusters. When we stack these galaxies that have, they are basically faint in continuum and have bright emission lines, we find that the average N2 to H alpha ratio decreases with increasing H alpha equivalent width. So it seems like this unique population of faint galaxies with high equivalent width or high specific star formation rate in merging galaxy clusters likely have very low metallicity. So these are probably low mass galaxies that are being triggered to form star formation now, and in time will build up their stellar mass and and will enrich the gas as well. But in order to really understand how star formation might be triggered in these galaxies, it's very important to have a resolved view, a spatially resolved view of these galaxies. To illustrate this, I'm going to use the example of the sausage cluster. This is a relatively low mass cluster at redshift of about 0.2. It is a very X-ray luminous cluster. You can see here in the background the X-ray emission of the cluster. And you can see that it has a disturbed morphology. And we believe that this cluster has undergone a twin merger between two clusters of almost equal mass about 0.5 to 1 billion years ago. And what this resulted in were like twin outward traveling fast shock waves that we can now detect in the radio through these diffuse radio sources. This cluster is very interesting because it is one of the most massive clusters we know of in the universe. It's 2 × 10 to the 15 solar masses, but it also hosts a spectacular overdensity of star-forming galaxies, above 20 times a typical field. And together with Miriam Husseini, an undergraduate at UT Austin who worked with me as a summer student in 2019, we followed 5 galaxies in the sausage cluster with resolved optical integral field spectroscopy, providing us for the first time a resolved view of these possibly shocked cluster galaxies. And let me share with you some of the insights that we got from this result spectroscopy. I mentioned we have 5 galaxies. 3 of them, sausage 5, 6, and 7, are firmly classified as star-forming spiral galaxies, while sausage 8 and 9 are dominated by AGN. We also have measurements of H-alpha flux, and all galaxies present slight offsets of H-alpha emission compared to the stellar disk of the galaxy, with tails of emission outside of the stellar disk. Galaxy kinematics are also very different. The H-alpha kinematics I'm talking about here. The ionized nebular gas in sausage 5, for example, has an asymmetric rotation pattern with higher amplitude and velocity on the approaching side. In sausage 7, for example, the ionized gas maps look remarkably different from the stellar distribution. The bright nucleus surrounded by a well-defined spiral structure is not necessarily reflected in the complex, clumpy H-alpha gas whose bow-like distribution is offset north from the stellar disk. From the N2 to H-alpha ratio, we can also calculate gas phase metallicities for the star-forming galaxies. And we know in both field and infalling galaxies, galaxies tend to have negative metallicity gradients from the center of the galaxy to the outskirts. Our galaxies present very atypical metallicity gradients, which tend to be more aligned with the stellar disk and the ionized tails of the galaxies, and possibly the merger cluster, the cluster merger axis, rather than go down with radius compared to the galaxy center. Now, these fast-traveling, relatively low Mach number shock waves, such as those produced in these cluster mergers, possibly compounded with the time-dependent tidal fields in these merging galaxy clusters, can result in elevated pressure, which compresses the interstellar medium, not only at galaxy outskirts, but also deep within the galaxies, and can result in galaxy-wide star formation sustained over 100 to 500 million year timescales. And the features that we observed in these galaxies in the flux, velocity, and metallicity maps are can be broadly ascribed to this scenario. So we find for the first time a possible direct connection between cluster mergers and star formation triggering. But as I mentioned, if disturbed galaxy clusters have a lot of star formation on these short timescales, through H-alpha, we know that on 1 to 10 million year timescales, they form stars. Maybe it's because we're primarily seeing trigger star formation in infalling galaxies. However, this is unlikely since the galaxies are embedded very deep within the intercluster medium. But nevertheless, do these galaxies have star formation sustained on longer timescales? And as I mentioned, we can correlate H-alpha emission to radio emission to see whether there's any correlation between star formation averaged on 10 million year timescales and star formation on 100 million year timescales. And what we find is that a larger fraction of the cluster star-forming galaxies have evidence for radio emission, so for radio supernovae, compared to galaxies in the field around the cluster. So it seems like galaxies that are located within the cluster have sustained star formation for 500 million years, whereas galaxies around the cluster might be the ones that are just kind of coming on right now. They have something that's triggering star formation in them as they maybe are infalling into the cluster. But again, this is very different from what is happening in the cluster, where somehow these galaxies have been triggered to form star formation well in the past 500 million years ago. But maybe, all of these star-forming galaxies in the cluster have used up all of their gas. Do they even have any fuel left for future star formation episodes? Maybe we're just kind of seeing the end of their life cycle. They've already used up all of their gas. And as I mentioned, we have H1 and CO at our disposal to be able to look at these gas reservoirs. And first, I conducted a survey of H1 to get a handle on what is the average neutral gas in these star-forming galaxies in this particular emerging cluster. And what we found was very surprising. We found that cluster galaxies, cluster star-forming galaxies, have just as much neutral gas as field counterparts around the cluster once you account for their different stellar mass. And this was very surprising because studies of local relaxed galaxy clusters have found that if you take a galaxy of a particular stellar mass and you move it from the field towards the cluster core, it becomes more and more deficient in neutral gas. And of course, this can be interpreted by the scenario of ram pressure, in which a lot of the gas is being removed from the galaxies and they become more and more deficient as they get closer to the cluster core. However, this is not what we observed in these merging clusters. But you might say, Andra, neutral gas doesn't matter anyways, because it's not the phase that is directly feeding star formation. And I will agree with you. And I think molecular gas is a great thing to look at as well. And together with Joe Cairns, we worked on a project looking at molecular gas. And Joe worked on this project as part of his PhD at Imperial College London. And together we conducted this very large survey of Antlia. Antlia is a very interesting cluster because it is the closest disturbed galaxy cluster. So it has exquisite multi-wavelength observations, coming from higher redshift to lower redshift is fascinating to me. The level of detail, like you can have amateur astronomers taking optical images of this cluster. It's so nearby. It's really fascinating. And this enabled us to really follow up very quickly a lot of galaxies in this cluster. So with molecular CO221, we covered over 70 galaxies, understanding the molecular gas reservoirs in galaxies on the main sequence and below the main sequence. And we covered basically a complete sample of galaxies limited in stellar mass and star formation rate. And we were also very fortunate to have a perfect field comparison for galaxies in the field from the Altsmach survey that followed up with the same technique, galaxies on the main sequence. And the main result of this paper is that we found that there is a single stellar mass star formation rate molecular gas plane on which both cluster galaxies and field galaxies sit on. To walk you through this plot, on the x-axis, you will have the stellar mass. On the y-axis, you have star formation rate. The color is showing you the amount of molecular gas, and the squares are showing you the field sample, and the circles are showing you the sample for the Antlia cluster. And you can see that the colors stay the same between the two samples, meaning that cluster galaxies have just as much CO as field galaxies of similar mass and similar star formation rate. Now, Antlia represents an intermediate environment between fields and relaxed clusters. And maybe this gentler environment is allowing galaxies to retain their molecular gas reservoirs. And this evolving intercluster medium might just be starting to interact with the cluster galaxies, producing the first evidence of gas removal and high star formation rates. And, to put this all in perspective, it seems like these disturbed galaxy clusters have a large number of star-forming galaxies compared to fully relaxed clusters. They also seem to have different properties. The galaxies in these merging clusters have different properties from galaxies located in relaxed clusters and those galaxies located in the field. For example, merging cluster galaxies form stars at the same rate as field counterparts, whereas we see suppressed star formation in relaxed clusters. They also have evidence for sustained star formation on long timescales of 500 million years, and somehow they still are rich in neutral and molecular gas. And this kind of got me really wondering, these merging clusters seem to be very similar in some ways to clusters at much higher redshift, so high redshift clusters and proto-clusters that are still in the process of formation. However, there's some very glaring differences between the two populations, as low redshift mergers have a much higher mass and they have a clear intercluster medium. But, I would really like to share some of these similarities because I think they're very interesting. High redshift protoclusters can also be detected as highly star forming, and it can represent huge overdensities of star forming galaxies. And you can actually use very similar techniques, just the same narrowband technique that I used at redshifts, above 1 with H alpha and Lyman alpha to detect protoclusters as overdensities of star forming galaxies. Above redshift of about 1.5, clusters also form stars at the same rate as field counterparts. It has also been found that galaxies in high redshift clusters have high gas fractions and widespread molecular gas reservoirs, much like the ones that we observe in more nearby merging galaxy clusters. And in my group, we're also very interested in pushing the boundaries towards these higher redshift clusters as well. And together with Courtney Canning, who was a CFA master's student and will start her PhD at Durham University in the UK in the fall, we followed up the most massive galaxy cluster merger at redshift 0.9 with spectroscopy. And this is the El Gordo cluster. El Gordo is very interesting to me because it is one of the most, it's the most massive cluster at high redshift. It is also a massive merger, and it's also high redshift cluster. So it sits at an intersection between multiple axes that make it a very interesting object. And I really encourage you to be on the lookout for Courtney's paper that will be out later this year. And she will present all of these infrared IFU observations focusing on H-alpha emission in the cluster, highlighting some of the interesting star formation properties in this massive high redshift merging cluster. The detailed spectroscopic analysis of the Anisala survey combined with gas tracers is really good because it enables us to break degeneracies between different models that have been proposed for galaxy evolution in clusters. As I mentioned, we unveil that the overwhelming majority of bright emission line galaxies powered by either star formation and AGN activity actually tend to populate the central 3 megaparsec region of merging clusters. Merging clusters also seem to host highly star-forming galaxies embedded deep within their hot intercluster medium plasma. So it seems like there's a correlation between cluster growth and which effects or each model, let's say, is the strongest or most relevant. Our results, for example, are readily explained by the model proposed by Ebeling in 2019, in which gas-rich galaxies infall along filaments in the rich cosmic web that's surrounding merging galaxy clusters, and this is followed by triggered star formation. The disrupted merger environment is, as I mentioned, permeated by shocks, turbulence, and strong gravitational tidal field, which can act as a catalyst for triggering star formation and as well funnel gas into the galaxy core, causing accretion onto the black hole and promoting AGN activity, much like what we observed in the outskirts of relaxed clusters. This scenario can also lead to a sharp rise of star formation happening for about 100 to 500 million years, which is very compatible with the high specific star formation rate galaxies that we tend to find almost exclusively in merging galaxy clusters. By contrast, we find evidence of mild enhancement of AGN and star formation at outskirts of relaxed clusters, followed by a dearth of star formation towards their core. These observations corroborate the extensive literature in the field that invoke that mild ram pressure and other processes can trigger activity at large cluster centigradi, but this is followed by very rapid quenching, taking over as the galaxies are infalling into the cluster, especially as they cross the cluster core. So it seems like the star formation black hole activity correlates with cluster merger timescale. So it seems like although clusters might go through very interesting episodes of star formation, the total stellar mass added is actually relatively small. It's about 1 Milky Way's worth of stars, but spread between 100 galaxies. So if you wait too long and you just observe your relaxed galaxy cluster in the local universe, it might be difficult to tell that the cluster in its younghood might have gone through a very interesting episode of star formation. But still, we have a lot of questions about, what is really triggering this star formation and what is regulating the flow of gas in and out of galaxies, and how is this black hole activity being triggered? And I'm also very interested in answering the question of kind of when did the intercluster medium actually form, and how does it evolve, and how does this become important for galaxy evolution in clusters? And I really want to explore more how these low redshift clusters can help elucidate processes happening in high redshift proto-clusters. And to answer some of these questions, over the past 2 years, together with my international collaboration, built a set of multi-wavelength observations that is really uniquely designed to reveal the 5 billion billion years of galaxy, black hole, and gas evolution from the perspective of cosmic structure formation. And by capitalizing on these, we're already awarded observation and the treasure trove of well-characterized cluster samples that are now being provided by eROSITA and LOFAR, we can really understand clusters in the more nearby universe to the detail that is necessary to provide the calibration parameters for the physics of high redshift objects. And, by leading the development of tools and predictions necessary for exploiting this new generation of instruments, we will be able to study physical processes occurring over a broad range of spatial scales in a coherent manner and really be prepared for new generation instruments. And since I'm mentioning new generation instruments, I'm very excited for the next years to come. The future for the field is so bright. In the 2020s and 2030s, we will have these new generation instruments working in concert, and it is very exciting to me to be able to hopefully take advantage of the unique synergies between these different instruments. On the X-ray side, we will have ATHENA and maybe Lynx. In the optical and infrared, we will have on the ground ELT and GMT. They're being, starting to be built right now. And in space, we will have Euclid and hopefully James Webb all the way into the 2030s. And of course, on the other side of the spectrum, we have the SKA coming towards the late 2020s as well. And I would like to just focus a little bit on X-ray, and it's really exciting with ATHENA and Lynx on the horizon, with a unique combination of collecting area, field of view, and resolution. ATHENA and Lynx will undoubtedly be revolutionary for many areas of astrophysics, but they will be particularly good for galaxy clusters. For example, ATHENA's capabilities are uniquely suited for the study of galaxy clusters in the cosmic web, and Lynx will have superb capabilities for unveiling the physics of black holes. And I'm very excited for the synergies between these X-ray instruments and radio observatories, LOFAR and SKA, for example. We will be able to unveil the cosmic web through shocked worm-hot intergalactic medium around galaxy clusters with SKA and ATHENA, and we'll also be able to unveil filaments, for example, with Lynx, which will map a 10 square degree area around the massive low redshift cluster as part of its legacy field. And it will also be able to really understand the thermal and non-thermal components of the intercluster medium and constrain things such as shocks, turbulence, magnetic field, pushing the boundaries to higher redshift, but also tracing clusters from cluster cores all the way to cluster outskirts, where these processes might be very relevant. At the highest redshifts, for example, beyond 2, Lynx will have the necessary angular resolution to resolve point sources and diffuse emission, and unveil to us the thermodynamic and kinematic properties of these earliest systems, as well as determine what the role of feedback is from AGN and stars at high redshift. And as a multi-wavelength astronomer, I am particularly interested in really putting together things from the entire spectrum, and from the perspective of galaxy and black hole evolution, it will be really fantastic once we have these multi-wavelength observatories working in concert, specifically on the ground with the GMT, for example, or with new generation VLT instruments. Studies such as the one that I presented today, Anisala, will be made very easy, not only in the local universe, but also at higher redshifts. We will be able to measure galaxy dynamics, masses, the detailed physics, metal enrichment, gas reservoirs, black hole physics in low mass clusters in the local universe, but also at high redshift clusters, and also unveil galaxy evolution in cosmic filaments that we know are so important for pre-processing what is happening in these sources. And I would like to kind of just convey to you as a final message that evolving from a field to a relaxed cluster environment involves accretion, collapse of filaments, and mergers, a very energetic process. And these cluster mergers are an important population which displays a reversal of the typical environmental trends we see in relaxed galaxy clusters in the nearby universe. And we believe that these mergers might be able to tell us something about high redshift clusters that are not so easy to study and not so accessible with current instrumentation. I'm very excited for the next 3 years, where I will explore the Anisala Survey and all the spectroscopy that we have to understand the detailed physics of star-forming galaxies and black holes. And in the next 10 years, as new generation radio and X-ray telescopes will come online, we will be able to place galaxy evolution and black hole physics in the context of the intercluster medium and the filamentary structure that surrounds clusters. And with this, I will say thank you. And if you have any questions, please feel free to ask. Thank you.
Thank you, Andra. And of course, one of the other things that we miss in this environment is that we will be giving a round clapping applause right now if we were actually all in the room together. So we're open for questions. I noticed a couple of hands up already, so that's great. So if you could have a question, please use the hand raised feature. If you prefer, put a question in the chat and I'll read it out. But you should be cautioned that I have a bad history of ignoring the chat through inattention. So, but I'm going to take advantage of my position here and ask the first question. So there's this feature that you mentioned earlier in your talk and came back to a number of times, which seems kind of obvious, that you have in these relaxed clusters, you have the red and dead galaxies at the center, and in the outskirts you have these gas-rich galaxies. Should I infer from that? Should we infer from that those gas-rich galaxies have never been through the central region? That they're either recently joined or they're on circular orbits or whatever?
I believe the consensus in the field is that indeed, if you have a galaxy and if it already crosses the cluster, if it goes all the way to the center, the bulk of its gas is removed. So indeed, we believe in of course, we don't have the 3D information all the time, which would be fantastic, but we believe that even if you see in some of these relaxed clusters, some of the galaxies be in projection towards the core of the cluster, they're actually in 3D behind and in front of the cluster, and they're kind of just maybe infalling into the cluster right now.
Okay, very good. So the first hand to go up is John Z.
Hi, John.
Please unmute yourself.
Yes, hi, Andra. Great talk. So totally quote unquote hypothetical questions. So based on all of the amazing observational data you've showed, if you had a wish list for simulators, if you could say, hey, I think you should do a simulation which incorporated all of this stuff to explore some of these observations, what would it be?
Oh, thank you so much. This is actually something that I thought about a lot, and I feel like the simulations that I would need are there, but maybe the simulation data is maybe not always presented or interpreted from the perspective that I'm most interested in. So I would really love to see, for example, results from simulations on what is happening in an active merger. I feel like there's a lot of discussion of field galaxies in our simulation and what is happening in this. We have this massive relaxed cluster in our simulation box. So I would be really interested to see these star forming properties, and maybe particularly, and I have no idea how difficult it is to actually do these simulations in a large box, but molecular gas and neutral gas, I would be really interested to see in a kind of cosmological, realistic galaxy. I know I have a big wish list. I don't think you can do all of these things, but if it would be possible to also have non-thermal processes there, have like shocks and predictions for radio. I know this is a big wish list, but one can only hope. You did say I can really, splurge.
Okay, thank you.
Thank you very much.
Okay, thank you, John. Igor, your hand's up. You're recognized.
Yeah. Okay, I have a question regarding the RAM pressure and galaxy orbits. So basically, we have recently identified a population of galaxies in coma that have undergone RAM pressure very recently. Now they're quenched, but they have tails still visible, and we can see very young stars in large quantities. So there was a RAM pressure induced star formation event. Interestingly, none of them is on a radial orbit, which we can see by the direction of tails. So did you try to check the orbital shapes? You know, as a first approximation, you can just plot them on the acoustic plot for cluster. Of course, acoustic for an unrelaxed cluster is hard to build, but still, you can at least have some indication. Have you tried to check whether your star-forming galaxies are on orbits with substantial tangential components?
Yeah, that's an excellent question. And I was wondering, what type of data do you have for the tails pointing?
So,
do you have IFU observations?
Okay, let me tell you here. Right now, we were concentrated on the galaxies themselves, and we have binospec. Short slit, not long, but short slit, because it's common. You can do many galaxies at once. But for one object that is very similar at a slightly lower mass in Virgo, I found an archival unpublished Muse dataset. And there is a completely quenched dwarf with an H alpha tail. And so basically you can infer star formation from the tail, but what we infer from the spectra is the amount of young stars formed during the last 400 million years. And it's up to 30% of the total stellar mass in a galaxy.
No, this is extremely interesting. So we do have the narrowband, which it's very difficult to subtract an image plane, the narrowband and the broadband, which would give us a sort of idea of the tails and what the H alpha tails are doing. I would love to, these are ground-based observations, and it's seeing limited. So it would be fantastic to have more HST observations. And actually I'm thinking about exploring to see, because I'm sure there's some observations already in there in the archive that could help with just highlighting these tails a little better. So we can't do this at least very well with the imaging that we have. And the only data that kind of gives us ideas of, which directions are the tails moving are just these 5 galaxies that I presented today. We don't really have, as you know, IFU surveys are very, very expensive, but, fingers crossed, I'm planning on putting a large project with Gemini. So the Gemini gods, if they're there and they're listening, if they could give us, a sample of more galaxies so that we can really get a better constraint, because these were just, it was a pilot study of 5 galaxies. And, by putting them on a kind of a position velocity diagram, they seem to be very close to the cluster core compared to, your typical, for example, jellyfish or tailed galaxies that you find in more nearby clusters. So that's why I mentioned that they're kind of really close to the cluster core, but they don't have like extreme tails of H alpha to really say, oh, this galaxy is definitely in falling this way or another. So they're not as extreme as some of these, I don't know, ESO, I forget the number of it, the ones that have like, So they're not extreme to that point for sure. But, I do have to say that by design, we did select these galaxies through the narrowband to be star forming. Now, is the star formation happening slightly outside of the galaxy or inside the galaxy? That's for this, we need more resolved information, because from the narrowband, we're just, we take the magnitude in the narrowband, the broadband, and we do a subtraction. But of course, the stellar disk and the star formation might not necessarily be co-located.
Okay, thank you. And a spoiler alert, there will be an IFU on binospec, hopefully by the end of the year.
That's very exciting to me. Thank you.
Yeah, so I think we can take a little longer. We'll take questions from Erwin and then Jonathan. Erwin, you're on. You're muted at the moment.
Yes, it would be well to unmute. Can you hear me now?
Yes.
Yes.
Yeah, I may have missed this because I had to do something for the family in the middle, but I was curious as to what you expect to learn about the effects of dark matter on merging clusters.
I think maybe I would pose the question slightly differently. Not necessarily that dark matter influences mergers in any way, but mostly that we can use mergers to understand dark matter. And there are a couple of people at the CFA that know much more about this than I do, but the idea would be that when you have one of these cluster mergers, because dark matter tends to interact only gravitationally, it just kind of goes through. And where the dark matter is from surveys of where the galaxies are, because the galaxies galaxies follow the dark matter. But then, of course, the gas, the intercluster medium tends to kind of stick to the center. The idea would be that, especially when you have these shockwaves, for example, that are produced when the cluster is merged, you can get a lot of constraints on the merger history of the cluster, and then you can compare the position of the BCGs, the gas, and all of these different components to tell you how, well, for example, I know people have attempted to put an upper limit on the cross section of dark matter, but I think you should, I can give you a couple of references of people at the CFA that are really working on this in much more detail than I am.
Thank you.
Okay, so Jonathan.
Yeah, Andra is a little peripheral to the main thrust of your talk, but I was kind of fascinated by these radio structures on either side of the merging cluster. And I was wondering if, so you have a brightest cluster galaxy that may be an AGN, or two, and you have a couple of these radio structures on either side. If you didn't have redshifts, you might think, in a radio survey, you might think that this was an FR2 or something like that. And so I'm wondering if we might be missing some of these objects by misidentifying them.
I think this is one of the main things that, for example, something like LOFAR will be great at, because it's going to detect a lot of these like weird diffuse sources that historically have been difficult to detect, particularly because a lot of telescopes are kind of geared towards resolution, and they're resolving out these super large structures on the sky. So they're, one megaparsec, they're, tens of arc minutes on the sky. Now, the argument for why we believe that they have to be kind of accelerated in situ is that, as I mentioned, if you did have an FR, it would have to be, first of all, like a huge FR1, we would have to find the host galaxy for it. And if it would be in the cluster, it would just be, I don't know, it would be like Nobel Prize. We found the most.
Yeah, I agree. I think this is clearly not that, but I'm saying if you scrap your data, you might think it was that.
Oh, well, usually, of course, if whenever we claim that these are shock associated sources, you usually do not make this claim based on a single frequency. So we have multi-frequency observations that help us, make sure that it's actually there, that is detected. We can constrain its spectrum, and you always check for possible point sources that might be, as you mentioned, like maybe, one of these, one of these arcs here might be associated with a particular source. And more modern models do think that you could have maybe an active galaxy. It used to be active in the past. It has aged. You don't necessarily see it in the radio anymore. And then you have the shockwave, and it kind of revives or reaccelerates the particles, because it's very difficult to get as much radio emission as we're seeing if you're just accelerating particles directly from the intercluster medium. So indeed, we believe, I think the more modern view is that there is actually a connection to some AGN activity in the cluster.
Thank you.
My pleasure.
So we got one last hand up. It's Bill and Christine, one or both.
We're both here. We both think it was a great talk. Thank you, Andra. My question is sort of related to some of the earlier questions as well. And you showed beautiful correlations between the merging and the relaxed clusters and the galaxy properties with the H-alpha and the AGN activity. And I was wondering whether even maybe perhaps with the help of the simulations, you could take this to a next step as far as dividing them more finely. So for example, for the relic clusters, the two subclusters have been through already. Whereas for perhaps some of the clusters where you see two well-defined subclusters, they haven't been through. And I was wondering whether that would allow you to make even more refined, properties and studies of the individual galaxies, when the star formation was induced, when the AGN activity was induced.
That is, yes. That's exactly what I'm hoping. So, today I just presented the first results of the survey, but of course we have, as I mentioned, 700 galaxies with spectroscopy, and we can measure much more than just equivalent width. We can measure line ratios that tell us something about metallicity. So there's much more physics and chemistry that is encoded in the spectra, and I believe it would be really interesting to be able to, as you mentioned, correlate these galaxies with the properties of the cluster as a whole. And for some of these mergers, for example, they're very detailed, tailored simulations that are trying to understand, okay, what is the merger history of this cluster? When did these two clusters collide with each other? And then we can make much more detailed correlations. But I agree, the data is very rich, and we have even the simulations that we need to do this.
Thank you.
Thank you. So I did say that was going to be the last question, but I did catch one from the chat. So I'll just read from Steve Wilner. He's asking, do you have essentially it's the equivalent of three-dimensional distances in some of these structures? Do you have radial velocity information that you can attribute to Hubble distances? Or do you really just have a two-dimensional projection?
Well, we have spectroscopy. If you consider that to be true 3D measurements or not, I think is up for debate, because of course they're in the cluster, so that kind of dominates their movement.
Yeah. Okay. Well, thank you very much, Andra. It's something I look forward to with eager anticipation. They play lecture every year, and you absolutely delivered for all of us. So thank you very much.
Thank you so much.
Let's all do a virtual clap. Not the same thing, but the best we can do.
And even real claps. Thank you very much.
Thank you. And thank you to Lavinia and Thomas for making time in your schedules to join us. Okay. Thank you very much, everybody. This is the end of the Clay lecture for 2021.